There's a flying machine you've probably been inside dozens of times that gets hit by lightning roughly once a year. And most of the time, nobody on board has any idea it happened. That's not an exaggeration. The average commercial airliner is struck by lightning at least once every 12 months in regular service, and many get hit 2 or 3 times a year. Right now, as you're watching this, somewhere on this planet a passenger jet is being smacked by a bolt, carrying around 300 million volts and roughly 30,000 amps. And it just keeps flying. Think about that for a second. The wiring in your home runs on 120 volts. A lightning strike is roughly 2.5 million times more powerful than your wall outlet. It's hot enough at its core to be about 5 times hotter than the surface of the sun. And we routinely fly fragile-looking aluminum tubes full of human beings directly through the storm clouds where this stuff is born. So how on earth does that work? How is it that something with that kind of raw power, hitting a vehicle made partially of plastic and composites, doesn't just rip it apart and send everyone to their doom? The answer is a layered, almost paranoid system of engineering tricks. And today I'm going to walk you through the 6 most important defenses commercial planes use against lightning, in order, from the coolest to the absolute most genius. Stick around, because the number 1 is the principle that makes all the others possible. But first you have to understand why aviation engineers became so obsessed with lightning in the first place. And to do that, we need to go back to a stormy night over Maryland in 1963. On December 8th of that year, Pan Am Flight 214, a Boeing 707 named Clipper Tradewind, was holding in a stack of aircraft west of Philadelphia, waiting for strong surface winds to die down so it could land. It was raining. There were thunderstorms in the area. At 8:58 p.m., a bolt of lightning struck the aircraft. The pilot of another airliner holding 1,000 feet above heard the radio call come through. Mayday, Clipper 214 out of control. Here we go. And looked down to see Flight 214 falling out of the sky in flames. Investigators would later determine that the strike had ignited fuel vapor inside one of the reserve fuel tanks in the left wing. The wing exploded. A large section of it tore off in flight. The 707 went down near Elkton, Maryland, killing all 81 people on board, 73 passengers and 8 crew. The Civil Aeronautics Board's investigation into that crash is what fundamentally changed how aviation thinks about lightning. The Boeing 707 had been designed under regulations that didn't even mention lightning protection. It simply wasn't a requirement back then. After Flight 214, that changed forever. The FAA ordered static discharge wicks installed on every commercial jet flying in U.S. airspace. New rules were written for fuel tank bonding, vent systems, and electrical shielding. 60-plus years later, those rules, refined again and again, are the reason your last flight through a thunderstorm probably felt boring. To this day, that 1963 accident is still officially listed in the Guinness Book of Records as the worst death toll from a lightning strike. And it remains the last time a lightning bolt brought down a commercial airliner in the United States. All right. With that out of the way, let's count down the 6 defenses that make modern airliners essentially lightning-proof. Number 6. Those tiny little spikes you've probably seen on the wings. If you've ever sat in a window seat and looked out at the trailing edge of the wing, especially around the wingtip and on the tail, you might have noticed little black spikes sticking out into the air. Those are called static wicks, or static dischargers, and they're one of the simplest yet most elegant pieces of equipment on the airplane. Their job isn't actually to stop lightning. It's to prevent the conditions that make a lightning strike more likely in the first place. Here's what's happening. As an airplane flies, friction with the air builds up massive amounts of static electricity on its surface. The same kind of charge you get rubbing a balloon on your hair, except scaled up enormously. If that static charge isn't dealt with, 2 bad things happen. First, it can interfere with radio communications, creating annoying noise on the headset. Second, and much more importantly, a highly charged aircraft is essentially screaming "come and get me" to any passing thundercloud. The plane becomes a more inviting target for a discharge. Static wicks fix this by giving the static a way out. They concentrate the electrical charge at their pointy tips, and from there it bleeds harmlessly back into the air. It's almost like an automatic pressure relief valve for electricity. Cheap, passive, no moving parts. They were one of the very first lightning-related modifications mandated after Pan Am 214, and they've been on every commercial jet ever since. Number 5. The lightning rod's built into the nose of the plane. Walk up to the front of any modern airliner and look at the nose cone. That smooth, rounded, painted dome that sits in front of the windshield. That part is called the radome, and it's not metal. It's made of composite material, usually fiberglass-based, because the weather radar that lives behind it has to be able to see through it to scan the skies for storms. A solid metal nose would block the radar completely. But here's the problem. The nose is one of the spots where lightning is most likely to attach. It's a sharp leading edge punching through the air. Without protection, a lightning bolt could blow a hole right through that composite dome and fry millions of dollars of radar equipment behind it. Or worse. So engineers came up with something brilliant. If you look closely at the radome, you'll see thin metallic strips running along it, often in segmented patterns. Sometimes they look like dotted lines made of tiny metal buttons. Those are called lightning diverter strips, and they essentially act as miniature lightning rods built into the surface of the nose. When lightning approaches, those metal segments ionize the air between them, creating a controlled path that carries the strike across the surface of the radome and back to the metallic structure of the airplane, without ever touching the radar inside. It's such a clever solution that it's now being adapted for other industries too, including on the carbon fiber blades of offshore wind turbines. If you're enjoying this so far, do me a favor, hit the like button and subscribe to the channel. It really helps the algorithm push aviation content like this to more people, and there's a lot more on the way. Number 4. How engineers stopped fuel tanks from blowing up. This one comes directly from the lessons of Pan Am 214. The reason that 1963 crash was so catastrophic wasn't really the lightning itself. It was that the lightning ignited fuel vapor in a reserve tank that was partially empty. And here's something that surprises a lot of people. An empty fuel tank is actually more dangerous than a full one. When a tank is full of liquid kerosene, there's very little airspace for vapor to form. When it's nearly empty, you get a perfect mixture of fuel vapor and oxygen. Basically a primed bomb just waiting for an ignition source. Modern aircraft attack this problem from multiple angles. First, every metal joint, fastener, and access panel on the fuel tank is bonded electrically. That means there's a continuous low-resistance path for electricity to flow across the structure, so when lightning strikes, the current doesn't jump across a gap and create a tiny spark inside the tank. Even 1 millimeter of arcing in the wrong place could ignite vapor, so engineers obsess over every single rivet. Second, lightning-tested sealants are used at every fuel system penetration. These are specially formulated to prevent any spark from reaching the fuel side of a fastener. And in many modern airliners, there's a third line of defense called fuel tank inerting. The aircraft pumps nitrogen-enriched air into the empty space above the fuel, lowering the oxygen concentration to a level where combustion simply isn't possible anymore. No oxygen, no fire. Even if a spark somehow did occur, you can thank Flight 214 for these protections. They were paid for in lives, and they're the reason fuel tank explosions from lightning have effectively been engineered out of modern aviation. Number 3. The invisible armor protecting your flight computers. A lightning strike isn't just a problem on the outside of the airplane. The electromagnetic pulse it creates can induce voltage spikes in any wire it passes near, even without touching it directly. That's potentially catastrophic on a modern airliner, where literally every flight control surface, every engine, every navigation system, and every cockpit instrument is run by computers connected through miles of wiring. If those induced surges reach the avionics, you could lose flight controls, displays, autopilot, pretty much everything. So aircraft designers wrap critical wiring in braided metallic shielding, like a flexible chainmail sleeve, that absorbs and grounds out electromagnetic interference before it can reach the wires inside. On top of that, sensitive electronics are protected by surge suppression devices, specifically components called transorbs that act like one-way valves for excess voltage. The instant they detect a spike, they clamp it down and dump the energy to ground, faster than the spike can damage anything downstream. The result is that even when a multi-million-volt lightning bolt hits the airplane, the pilots in the cockpit might see a brief flicker on a display, or hear a loud bang, but the airplane itself keeps flying perfectly normally. Tell me in the comments, have you ever been on a flight where you actually felt or heard a lightning strike? I'm genuinely curious how many of you have noticed one. Number 2. The copper hidden inside modern composite jets. Here's where things get really clever. For most of aviation history, lightning protection was almost a freebie. Aluminum is an excellent conductor of electricity, and the entire fuselage of older airliners, the 707, the 727, the 737, the older 747s, was basically a giant aluminum can. That metal skin naturally distributes any electrical current across its outer surface and away from the interior. But starting in the 2000s, things changed. The Boeing 787 Dreamliner, which entered commercial service in 2011, was designed with a fuselage made roughly 50% from carbon fiber reinforced plastic. The Airbus A350, which arrived shortly after, uses similar composites. These materials are stronger and lighter than aluminum, which means better fuel efficiency and longer range. But there was a serious catch. Carbon fiber is much less conductive than aluminum. A lightning strike on a pure composite skin could burn straight through, blow chunks off the airplane, or worse, conduct enough current into the interior to fry electronics or ignite fuel. The solution is one of the coolest pieces of materials engineering you'll never see. Embedded directly into the outer layers of the composite fuselage on aircraft like the 787 is an extremely fine mesh, sometimes copper, sometimes aluminum, sometimes a hybrid wire-woven fabric that mimics the conductivity of an aluminum skin. When lightning strikes, the current spreads through this hidden mesh just as it would through a metal hull, distributing the energy across the airframe and dumping it back into the atmosphere through static wicks at the wingtips and tail. You will never see this mesh from the outside. It's buried under the paint, under the surface films integrated into the very structure of the airplane. But without it, modern composite airliners simply could not exist. And the number one, the principle that makes everything else work, the Faraday cage. Everything we've talked about so far, the static wicks, the diverter strips, the bonded fuel tanks, the shielded wiring, the copper mesh, all of it is in service of one single, beautiful idea. An idea that was discovered nearly 200 years ago, in 1836, by a British scientist named Michael Faraday. Faraday demonstrated something extraordinary. If you take any conductive enclosure, no matter what shape, and apply an external electric field to it, the charges inside the conductor will rearrange themselves in such a way that the electric field inside the enclosure becomes zero. The current flows around the outside of the cage. The interior is completely protected. He famously sat inside one of these cages while massive electrical discharges crashed against the exterior and felt absolutely nothing. The same demonstration is still done today in physics museums around the world, where a presenter sits inside a metal cage while an enormous Tesla coil hurls visible bolts of electricity at it, and the person inside might as well be sitting in a coffee shop. That principle is what every commercial airliner relies on. The aluminum fuselage, or the copper mesh-embedded composite fuselage, forms a continuous electrically conductive shell around the entire passenger cabin. When lightning strikes, the current does not pass through the cabin. It flows along the exterior skin, finds an exit point, usually a wingtip or the tail, and leaves the airplane through the discharge wicks. Inside the cage, you and the pilots and all the avionics are protected by physics itself. Every other defense on the airplane exists to make sure that Faraday cage stays intact. The diverter strips keep the current on the surface. The bonded joints keep it flowing without sparking. The static wicks give it a way to leave. The copper mesh recreates the cage on aircraft that aren't naturally metallic. It's all one system, and Michael Faraday figured out the core principle in 1836, decades before the first heavier-than-air flight. This is why, despite tens of thousands of lightning strikes hitting commercial aircraft around the world every single year, we haven't lost an airliner to lightning in the United States since 1963. 60-plus years, layered engineering, hard-earned regulations, and a principle of physics from the early 1800s. Together, they've turned what should be one of nature's most terrifying threats into a non-event you usually sleep right through. But if this impressed you, wait until you see what happens when an airplane flies into something even more violent than a thunderstorm. The kind of severe turbulence that can throw passengers against the ceiling, and how engineers design wings that flex through it without breaking. That video's already on the channel, links right there on the screen. Go check it out, and I'll see you in the next one.